Hi, everyone, and welcome to our ISPI Vaccines Special Interest Group Indoor Symposium. COVID-19 vaccines, some of them actually have more than one dose to complete the vaccination schedule. And so our symposium today is about the methodological approaches to evaluating the safety and effectiveness of these multi-dose COVID-19 vaccines. I'm Hui Li Wong, Associate Director of Innovation and Development at the Office of Biostatistics and Epidemiology, Center for Biologics Evaluation and Research, CBER, US Food and Drug Administration. No disclosures. The FDA, the US FDA, conducts active surveillance of COVID-19 through the BEST initiative, through multiple partnerships. This includes commercial databases, for example, pre-educated database, which is Optum, and the public database in the US, and that's the CMS Medicare, that covers more than 92% of those above 65 in the US, electronic health records, and linked claims and electronic health records. We're currently now conducting a continuum of active surveillance of safety.
Some elements seem like they're...
This ranges from signal detection to where we have near real-time surveillance or rapid cycle analysis. We do this by vaccine brands and by dose. We get that a little bit later. If there are any signals from there, we verify them through pre-specified protocols publicly posted on our website. And we also conduct other influential studies. Our Office Director, Dr. Steve Anderson, will provide more details on this in the plenary session tomorrow on COVID-19 vaccines. Well, during the period of time that we're currently now conducting the active surveillance of COVID-19 vaccines, we have found that we have a number of considerations in terms of methodological approaches for these multi-dose vaccines. This includes a time in the scenario when they are actually during the period of time we attribute either the risk or effectiveness of the outcome. That's their interval, but that actually overlaps between two doses. So then the question then is that how do you actually attribute the risk or effectiveness to those? And how do you then actually attribute those schedules? For example, the difference, the length of these intervals. There's also considerations for immortal time bias in terms of misspecification of person time when you have contraindication of the next event in the subsequent dose, and also considerations of the performance of these rapid signal detection methods. Previously, we've seen a lot of just one dose, but now there's considerations of these multi-doses. With that, we're very pleased to be joined by our speakers here today. Our speakers here today have researchers and scientists working in various fields and other vaccines, and who will offer us approaches for COVID-19 vaccines here. Dr. Garcia de Arbenes Martinez, Dr. Butler, Dr. Whittaker, and Dr. Shushad, both will each speak for around 15 minutes. Will then be followed by 5 minutes, question answer after each speaker, then a group session of question and answer with everyone. So we invite all the participants to please write in the chat box here anytime during this presentation to ask any questions, of which then we will then follow up with a question and answer session. We thank our ISPI SIG group and our BEST initiative. And for further information and publicly posted protocols, please go to the QR code and also our BEST website. With this, let's start with Dr. Garcia de Arbenes Martinez, who is Director of Epidemiology at RTI Health Solutions, coming to us from Barcelona, Spain. Xavi.
Thank you very much, Willie, for the introduction. Let me share my screen. Okay, I'm going to talk about different methods to assess different dosing of COVID-19 vaccines. And as a disclaimer, I'm an employee of RTI Health Solutions, and I don't have any conflict of interest related to this work. Let's get started with a few research questions as example of studying different dosing of COVID-19 vaccines. The first question, the first example would be, what is the effect on the risk of death? I just chose death as an outcome. You can choose your preferred outcome here. What is the effect on the risk of death of receiving a full vaccination schedule consisting of 2 doses in this case, compared with no vaccination. Another research question could be, what is the effect on the risk of death of receiving each of the possible COVID-19 vaccine dosing, 1 dose, 2 doses plus a booster, compared with no vaccination? Another example could be, what is the effect on the risk of death of receiving at least 1 dose of a multi-dose series of the COVID-19 vaccine compared with no vaccination? And the fourth example could be, what is the effect on the risk of death of receiving a booster of the COVID-19 vaccine compared with not receiving a booster? Why am I giving you so many examples? Because the first 2 examples are research questions where the exposure is sustained over time, as opposed to the other 2 examples where we are talking about a single time exposure. This is relevant because when the exposure is sustained over time, we are going to face more challenges when we want to estimate a valid effect of this strategy that is spread over time. So to see which challenges we can face and how can we address those, we're gonna do a thought experiment, and we are trying to design a study to answer this question. What is the effect of every possible dosing strategy compared with no vaccination? In an ideal world, we would run a randomized trial, of course, to try to answer this question, because this is the most valid approach to answer this research question. In our ideal trial, we would identify eligible unvaccinated individuals, and we would randomize them to each of the vaccination strategies. No vaccination, receiving a single dose, receiving 2 doses, and receiving 2 doses and a booster after the second dose. But of course, running this trial is hard. So when we cannot run a randomized clinical trial, we have to resort to the next best option, which is using observational data to try to emulate that target trial. Emulating a target trial stems on the principle that whenever we have a causal question, we should be able to design a hypothetical trial to answer that question. And designing that trial is just writing down each of the components of our hypothetical trial, and then try to figure out how we can emulate each of those components. And this is what I'm going to do here. For this target trial of 4 arms, where I want to compare every possible dosing of this hypothetical vaccine compared with no vaccination, my eligibility criteria would be unvaccinated individuals without contraindications. The vaccination strategies, that 4 arms that I'm gonna randomize people to, are the first, no vaccination, the second, just a single dose at baseline. The third arm would be a first dose at baseline and a second dose within, let's say, 3 to 6 weeks. Of course, in the absence of a contraindication. If somebody has an anaphylaxis to the first dose, nobody would give a second dose to that individual, right? And the fourth vaccination strategy would be a first dose at baseline, a second dose within 3 to 6 weeks, and a booster 8 months after the second dose. Again, always in the absence of a contraindication. In my target trial, we would randomize individuals to each vaccination strategy. My outcome is death. The follow-up starts at baseline and ends at death, lost to follow-up or administrative end of follow-up. And the causal contrast, I can estimate the intention to treat effect or the per protocol effect. In this case, I chose the per protocol effect because policymakers are probably more interested on what is the effect of actually receiving the vaccination strategy than just being assigned to that vaccination strategy. And for the statistical analysis, because I'm estimating a per protocol analysis, I will have to select the compliant person time somehow, and we can do that by censoring people when they deviate from the assigned strategy, and then use proper methods to adjust for that informative censoring. Sounds easy, but we are going to face 4 problems when we try to emulate this specific trial. The first problem is the multiple eligibility times. As you know, a key principle of emulating a target trial is alienating these 3 components. First, baseline, which is time 0 when I start counting my outcomes, the application of eligibility criteria, and the assignment of the exposure. This will save me from committing immortal time bias or prevalent user bias. Eligible patients in any of the vaccination arms have a very clear baseline. That baseline is the day they received the first dose. But eligible patients in the no vaccination arm can be eligible multiple times. So when should I include them in my study, in my emulation of the target trial? Here I have two choices. First, choosing just a single eligible time, for example, the first time they are eligible or a random eligible time. And the second choice, which is more efficient, is choosing every eligible time. How does it work? It works by emulating a series of nested trials, each starting at an arbitrarily chosen time unit. So this is how it works. This is a schematic representation of the emulation of a series of nested trials. Let's say I have my study period that goes from 1 year to another year. So the first time unit, let's say it's a week. The first week of my study period, I will select my bunch of eligible guys, and then I will classify them into one of the one or several of the vaccination strategies that their baseline data are compatible with. And that is going to be the beginning of my follow-up. That's my first nested emulated trial. Then I can move to the second week of my study period and repeat the process, apply eligibility criteria, vaccination strategy assignment, and the beginning of follow-up, and so on for as many weeks as I have in my study period. The second problem is that patients' data can be compliant with more than one strategy at baseline. For example, what if a person dies 2 weeks after receiving a first dose? That person is being compliant with 3 strategies, with a single dose, 2 doses, and 2 doses and a booster strategy. She died just here. The same with contraindications. What if somebody has an anaphylaxis after the first dose and doesn't receive any more doses because of the anaphylaxis? She's being compliant with the single dose, 2 doses, and 2 doses and a booster strategy. How can I solve this? I can either clone my sample, make copies of my samples, and assign those clones to the arms with which they are compliant at baseline, or randomize my sample to the vaccination strategies. And this is a representation in the research question that we are exploring. In the emulation of this trial, we would have a group of eligible individuals at baseline. Some of them receive a first dose at baseline, and some of them don't receive a first dose at baseline. Those that don't receive the first dose at baseline go to the no vaccination group. That's straightforward. But those that receive a first dose at baseline are being compliant with the single dose strategy, 2 doses strategy, and 2 doses and a booster strategy. I can address this by creating 3 copies of this individual and assigning 1 copy to each group, to each vaccination strategy. Because I'm estimating the per protocol effect, I want to select the person time that is compliant with each strategy. For the no vaccination group, I will do that by censoring individuals if they receive a vaccine during the follow-up. The same with the single dose group. If they receive any further doses, I will censor them. The clone that is assigned to the 2 doses group is censored if she doesn't receive a second dose by 1 month after baseline. And the same in the strategy of 2 doses and a booster. When they deviate from this strategy, we will censor them. And of course, as I mentioned before, if somebody has a reaction that contraindicates to the first dose that contraindicates further dosing, she will be compliant with the 3 strategies. We will not censor her. The third problem is not new for any of us. The third problem is baseline confounding. Those that receive a vaccine at baseline can be different from those that don't receive a vaccine at baseline. And if those differences are related with the outcome, we have confounding. All of us have faced this in our regular analysis of observational data. You just have to measure the confounders and use your preferred epi method to adjust for baseline confounding, because we are analyzing secondary data without baseline randomization. And the fourth problem is post-baseline confounding. Our causal contrast is the observation analog of the per protocol analysis, and we are introducing this artificial censoring to select the compliant person time. The truth is that this censoring can introduce bias because individuals that receive multiple doses of the vaccine can be different from those that receive just a single dose. And those differences can be present at baseline, or they might appear during the follow-up. And even worse, those factors can be affected by prior vaccination status. This is called treatment confounder feedback. When we have treatment confounder feedback, even if we have all the required information to estimate the average causal effect, we will need specific methods because traditional methods will fail to adjust for that. The methods, a set of methods that is useful here are called the G methods, and inverse probability weighting is a type of G methods. And it works by creating a pseudo population where treatment at each time point is independent of past treatment and past confounder. So that gets rid of the treatment confounder feedback under some identifiability assumptions. So as a summary, we had 4 problems. The first was the multiple eligibility times, which we addressed by emulating a series of nested trials. The second problem was that patients' data can be compliant with more than one vaccination strategy at baseline, and we addressed that by cloning. The third problem was baseline confounding. We deal with this every day, we epidemiologists. And the fourth problem was post-baseline confounding. And in this case, I'm proposing using inverse probability weighting to address that. Okay, so let me show you an example of the application of this approach, an example that is not on vaccines, but it contains the same structure. It gives us the same problems that I just enumerated before. In this publication, we address the following research question. In women of this age group that receive a screening mammogram at baseline, what is the effect of stopping screening versus continuing screening for 8 more years? This is parallel to a research question where we compare people that receive a single dose vaccine at baseline, and one group doesn't get any vaccine, and the other group continues getting vaccines doses over time. I chose this example because the exposure here is sustained over 8 years. So it's a pretty extreme example of an exposure that is sustained over time. So the first thing we did here was a naive analysis. We just compare women that received screening for 8 years versus those that didn't. And of course, this is a biased estimate because you need to be alive for 8 years to receive screening for 8 years. So the mortality in the screening group is close to 0. We would never do this here, the same way that we would never do this in a multi-dose vaccine study. We would never just naively compare people receiving 2 or more doses with those that didn't receive any dose. In this example, we follow the same analytical approach. We clone people, assign them to the strategies that their data were compatible with, and then apply artificial censoring and inverse probability weighting. And in this case, we got a hazard ratio of 0.78, which was in line with prior clinical trials. But I chose this example because, as I mentioned before, the exposure here was sustained for a very long period of time, 8 years. And in this case, adjusting for post-baseline variables was very relevant. In this graph, we can see the estimate we obtained when we ran an adjusted analysis. The hazard ratio was 0.38. Some of the effect was adjusted away by adjusting for baseline variables. But when we adjusted for time varying variables using inverse probability weighting, that's when the estimate moved much closer to the null. So at least in this application, adjusting for post-baseline confounding was very relevant. Okay, and just to finish, I have 2 slides left. I want to say a couple of words about case control studies. If you go to Ken Rothman's book, it says that a case control study is just a way to sample from an underlying cohort, which means that problems 1 to 4 that I presented before, multiple eligibility times, data compliant with more than one strategy, baseline confounder and treatment confounder feedback, those problems are also present in a case control study. Doing a case control study doesn't get rid of these problems. So if you're gonna do a case control study, for whatever reason, you need to have an underlying cohort that properly emulates a target trial. And you might wonder, so why on earth would I want to do a case control study if I had to construct the cohort anyways? Well, there are situations where you need to use limited resources to collect additional information on the treatment or on the confounders, and in those cases, it can be a useful design. So as a conclusion, studying different vaccine dosing can imply comparing vaccination strategies that are sustained over time. when we have an exposure that is sustained over time, we might face this treatment confounder feedback. And to deal with that, we need to use proper methods. And it's very important to align the beginning of the follow-up, the application of the eligibility criteria, and vaccination strategy must be aligned at the same time point to, to avoid committing immortal time bias. That's all. I have some references, and here is my email. If you have any question after this session, feel free to shoot me an email, and I will respond to you as soon as possible. Thank you.
Thanks, Zavi. And Mark, thank you for kicking the chat off. Please feel free to have questions for Zavi in the chat, and we'll answer that. I see we don't have any questions yet, so we move to our next speaker. We can have those questions at the end of our session. Our next speaker is Dr. Ann Butler, Assistant Professor of Medicine, Washington University in St. Louis, Missouri, USA. Ann?
Great, thank you for the introduction. So I'm really honored to be a part of the symposium today. And today I'm going to talk about methods to study the effects of the timing of vaccine doses in COVID-19 vaccine schedules. So here are my disclosures. And first, I'll start by just doing an overview of the recommended COVID-19 vaccine schedules in the US and define the vaccine schedules by sort of the vaccine formulations, the number of doses, and the timing of doses. And then I'll spend most of the time today talking about a real-world study example that uses an innovative approach to estimate effects of different multi-dose vaccine schedules. And this is a study that was recently published about comparative effectiveness of different rotavirus vaccine schedules. And this uses an inverse probability of censoring weighted estimation approach. And then I want to talk about how we can apply this approach to study COVID-19 vaccine schedules, and then talk about some of the challenges to extending this approach to study it in the here and now in 2021. So here are 3 of the recommended COVID-19 vaccine schedules in the US. The Pfizer-BioNTech, which was fully approved yesterday, was initially a 2-dose vaccine schedule, with the 2 doses recommended to be 3 weeks apart. Moderna, another mRNA, was similar, with the 2 doses recommended to be 4 weeks apart. And then the Janssen, the J&J, is a single dose vaccine schedule. And then last week, we were advised with the new recommendation to start getting a booster dose. For the mRNA vaccines, this would be starting 8 months after the 2nd dose. And then for Janssen, the J&J, we're still waiting for evidence review for the recommendations. And so, then let's think about these COVID-19 vaccine schedules. So these existing recommendations on vaccine schedules are based on evidence generated from very large randomized clinical trials, with 30,000 people or more. But real-world estimates of the effects of multi-dose vaccine schedules on health outcomes are needed to help inform vaccine schedule recommendations. And randomized clinical trials are useful, but do have limitations. For example, for our study on rotavirus vaccine schedules, we couldn't feasibly randomize 2-month-olds to getting 0, 1, or 2 doses of the rotavirus vaccine, for example, due to lack of equipoise. Also due to costs. For example, there are a limited number of protocols under study in these trials, so there's lack of head-to-head comparisons by formulation. There's often more focus on the number of doses and less focus on the timing of doses. And so non-experimental studies are useful to understand real-world effectiveness, but challenging due to the tremendous variability in real-world patterns of vaccine receipt. So one approach to study the effects of vaccine schedules is to determine the schedule that each person followed during a defined schedule ascertainment period, and then compare the risk of outcomes that occur after the ascertainment period between children on various schedules. However, requirement of a schedule ascertainment interval is problematic for several reasons. First, it does not permit study of outcomes that occurred during the interval. It possibly impairs generalizability because we restrict to study populations that are under observation for the entire schedule ascertainment. interval. And we possibly induce selection bias if the schedule itself affects the probability of being observed for the full schedule ascertainment period. So to address these issues, we aim to estimate the effectiveness of different vaccine schedules and compare outcomes among patients who followed different protocols. And we used an inverse probability of censoring weighted estimation approach and accounted for potentially informative schedule deviations. The method adapts an analytic approach originally developed to study protocol adherence, and the general approach has been used to study the effect of dynamic treatment regimens, to study the population attributable effect of preventing treatment discontinuation as well. So our first aim was to estimate the effects of varying levels of adherence to rotavirus vaccine schedules on the cumulative risk of two outcomes: acute gastroenteritis related hospitalization and emergency department visits during the first years of life. And I'll remind us that the rotavirus vaccine schedules are defined by vaccine type, number of doses, and timing of doses. And then our second aim was to estimate the population attributable effects representing the potential decrease in our two outcomes: age-related hospitalizations and ED visits, from a theoretical intervention that shifts the entire population from their observed real-world adherence of the recommended rotavirus vaccine schedule to full or perfect adherence. So we used a commercial insurance database in the US and created a cohort of infants and anchored the index date on the date of receipt of the infant's first dose of DTaP vaccine, diphtheria, tetanus, and acellular pertussis. The baseline covariates were identified from birth until the index date, so this green area here. And then the exposure receipt of rotavirus vaccination dose number 1 was assessed on the index date. So we used CPT codes to identify vaccine formulations. For rotavirus vaccine, RV1 here represents the monovalent formulation, which is a 2-dose series administered at 2 and 4 months of age. And then the pentavalent vaccine, which is here represented as RV5, is a 3-dose series recommended at 2, 4, and 6 months of age. CDC recommends doses to be administered during this timing. And during the follow-up period, we assessed these outcomes. So for each child, we created 6 copies of the longitudinal data set to correspond to 6 rotavirus vaccine protocols of interest. And here they are. And then infants were deemed non-adherent to a protocol and subsequently censored from that cohort when rotavirus vaccine receipt or non-receipt deviated from the protocol. And this is similar to what Dr. Garcia de Albanese just described in his previous publication, similar methods. So right now I'm going to focus on, just as an example, how did we classify person time for the protocol of people that were vaccinated with 2 doses of RV5. So here, an infant contributes person time to the protocol for the partial 2-dose series of RV5. And you can see this in the top line here, this child is adherent to this protocol, receives first dose of RV5 on the index date, and then a second timely dose of RV5, and then is followed until administrative censoring. However, this child would be censored from this cohort on the date of protocol non-adherence, defined as the earliest of the following: a 3rd dose of RV5, a 1st dose of RV1, different formulation, no timely 2nd dose of RV5, or too early a dose of RV5. So moving to results, so these figures, what they'll give you is weighted cumulative risk estimates on the y-axis here of our 2 outcomes: age-related emergency department visits and hospitalizations for the first 2 years of life, which is on the x-axis. And so this method yielded similar 2-year effectiveness estimates for the full series protocol. So you can see 2 overlapping lines here for the full series protocols: 2 of the 2-dose series and 3 of the 3-dose series. And also a dose response relationship wherein additional doses further reduce the risk of the outcomes. So for aim 2, these figures present the inverse probability of censoring weighted cumulative risk estimates for our 2 outcomes again. We've got cumulative incidence again on the y-axis by days since index date on the x-axis. And this method enabled estimation of the population attributable effects of a theoretical intervention comparing the observed real-world adherence, which is here in the dark gray, to full adherence of the recommended rotavirus schedule, which is denoted here in the light gray. So these results are subject to several limitations. The results may be subject to uncontrolled confounding. We accounted for baseline covariates only, not for time varying covariates. However, our unadjusted and weighted estimates were similar, indicating relatively little confounding or selection bias by measured factors. And second, our study was conducted under the assumption of no interference. That is, potential outcomes of one individual assumed to be unaffected by the exposure of other individuals. And this assumption does not hold because the risk of infection in one person depends on the distribution of vaccination in other members of the population. However, recent simulation results have shown that the bias due to interference may be small under even moderate levels of interference. And then third, we specified a single semi-parametric model for the probability of censoring due to not following a protocol at baseline and for not adhering to a protocol during follow-up. And we assume that the same set of covariates are sufficient to account for informative censoring due to either reason. Therefore, this approach will remain valid if the composite censoring model is correctly specified. However, models may be warranted for each source of censoring. Nevertheless, the similarity of our adjusted and unadjusted results suggests that the resulting bias may be small. So this approach that I just described that we applied to study the comparative effectiveness of different rotavirus vaccine schedules is applicable to study the comparative effectiveness of COVID-19 vaccine schedules. And depending on the real world patterns of vaccination, we can create different protocols based on both vaccine formulations. So here we can sort of we can compare protocols within each formulation, or we can consider mixing formulations, right? Like what if somebody gets the single dose of J&J and then gets a booster dose, for example, of one of the mRNA vaccines. We can also we can adjust the timing of our protocols. So here, for example, the mRNA vaccines, we're recommended to get the booster dose 8 months after the second dose. But other countries are doing different things, right? Like if we think about Israel and they're administering a booster dose more closely to the second dose, so a smaller interval between dose 2 and 3. If we can see that this pattern is occurring frequently enough in the real world data, then this is something that we can study. We can get at, estimate the effects of different timing of these protocols. But there are more challenges to consider when extending this approach to study COVID-19 vaccines in 2021 for sure. So critically, we need exposure assessment, so accurate capture of vaccine receipts, including type of formulation, date of administration. And this is potentially problematic in the US, at least, where many people are accessing or getting their vaccines outside of their typical healthcare setting. And so there are no insurance claims in the databases for their vaccination. Outcome assessment, it's important, of course, that we accurately capture our outcomes, whether they're COVID-19 infection or related hospitalization or ICU admission or death, which we would need for competing events anyway, especially in certain populations. And so national health insurance databases may be ideal for studying this. For example, if we could get our hands on the Israel data, they have a population of 8 million people, 98% of them have insurance, and then they have data that is really compiled together. So this is the type of data that would be really ideal for this kind of study. I mentioned interference before. Potential outcomes of individual may be affected by exposure of other individuals. You know, the big example right now is that unvaccinated children have a lower risk of COVID-19 infection if they're living in households with vaccinated adults. Their risks are lower of COVID-19. And this interference issue affects our ability to estimate certain types of vaccine effectiveness estimates, referring to indirect effects versus direct effects. And then another big challenge, of course, that we have to consider is confounding. We need the ability to identify baseline and time varying covariates that may predict vaccine receipt and be independently related to the outcome. So we can think about temporal and geographic confounding. We need information on history of previous infection, the population immunity, the proportion of the population who is immune is changing over time. We need to think about seasonality when in the hot and cold weather people tend to stay inside and the risk of transmission goes up. Our mitigation measures have changed over time from complete lockdown to schools closed, masking, and then now in some places, none of that being used, right? And then confounding by frailty, the original rollout was staggered first to frontline healthcare workers and the elderly and then persons with comorbidities, and we're going to have this same pattern occur again for the booster doses. So all challenges to consider when we're estimating these effects. So in summary, use of the inverse probability of censoring weighted approach to account for informative protocol deviations overcomes limitations of non-experimental studies that implement traditional EPI approaches to study vaccine schedules. And the approach demonstrates a method to evaluate the effects of the formulation, number, and timing of doses on health-related outcomes. So special thanks to my collaborators on this work and the funding sources, and thank you very much.
Thanks, Anne. Checking through if there are clarifying questions. Mark, would you, and there's some questions for Zabi that we will have during our panel question answers question. So, and Mark, would you like to ask that question?
I'd be happy to.
Oh, if there's time, I'd be happy to. And thank you very much for bringing up the ideas of sort of the changing background population immunity. And also, since this is an emerging infectious disease, also, you know, the population and geographic structure and infectivity. I'm really interested in what types of approaches you would consider in terms of measuring, or at least which measurements of these would be most important, and then how we can include them in our outcome models, or at least, you know, how you would think about doing that.
Right, and thank you so much for that question. And can you repeat the factors that you were most interested in? I think you said % of population immune. Yeah,
so it's the first is, I mean, you specifically mentioned there's changing population immunity, which changes transmission rates, but there's also changing population infectivity, so infection rate and how that changes over time in space.
Right, and so, you know, I think you're probably referring to the Delta variant, for example, which is much more transmissible than what we had before. So, you know, doing a study 4 months ago is different from doing a study right now where we've got mostly the Delta variant, right, which is more transmissible. I think that for addressing all of these issues that are changing over time, you know, for example, the proportion of the population that's immune, looking mitigation measures, all of these things that are changing. I think that one way to handle this is to account for calendar time in the analysis, whether we, you know, are using matching or weighting, trying to essentially match our exposed or match, you know, protocol 1, patients in protocol 1 to patients in protocol 2 within, you can do it within a month, a calendar month, so that you're estimating your effects, accounting for these, holding these factors sort of constant within the month. Does that answer your question, Mark?
No, I absolutely. I very much agree that sort of as a first order approach, we need to be taking calendar time into play along with geography, right? Because time in one place. Go ahead.
So this sounds interesting, but let's have this conversation with the rest of the panel in the question answer session. Thanks, Mark, and thanks, Anne. So our next speaker, and we have some questions that the rest of the questions we'll have in our panel discussion too. Our next speaker is Dr. Heather Whitaker, Senior Statistician, Public Health England. coming to us from London, United Kingdom. Heather?
There we go. Hopefully that should be showing correctly now. So just quickly run through my disclosures. Note the grants that the research was funded under, and but I've got no other disclosures. So I'm going to be talking about self-controlled case series methods, which have a long history of over 20 years of use in vaccine safety studies. So I'm going to kind of jump in fairly fast and only kind of introduce it fairly lightly. And I hope that most people do at least have a little bit of familiarity with what self-controlled case series method is by now. So the aim of a self-controlled case series analysis is to estimate a relative incidence, or if you prefer, an incidence rate ratio. And this is a factor by which an outcome rate is increased during a pre-specified exposure or post-vaccination risk window relative to unexposed baseline windows. So the method is making comparisons between windows of time within individuals rather than making comparisons between individuals. I'll just quickly run through the terminology I'll be using. So to look at the sort of windows post-vaccination where we might see that are hypothesized to be at increased risk, I'm calling the post-vaccination risk windows. And the baseline windows are all other time before and after these windows that we assume are kind of like a baseline risk. And the observation period is the period over which is like an individual study period. So for something like COVID-19, we might start at the beginning of the vaccination campaign, and then the end might be just the last up to date in the database data. It's perfectly valid to set up these observation periods in terms of any sort of calendar time, age, or they can be set up in relation to the timing of the vaccinations. So there's a little example of the kind of figures I might be putting in this presentation. So my vaccination risk windows, I'm putting in a color like yellow or possibly green, I think at times. And my baseline windows, I always have set up as gray. Those little red crosses might be my events, and then I indicate the timing of the vaccination with a little arrow. Here's an example of where it was, self-controlled case series was used in a study of mumps, measles, and rubella vaccine, looking at convulsions. So this is a plot where everything is lined up on the timing of the vaccination along the x-axis, and then we've got the count of the events up along the y-axis. So there's a little arrow there where the timing of vaccination is, and you can see this big spike 6 to 11 days after the vaccination. So there were 2 risk periods set up after vaccination for this particular study, 6 to 11 days and then 15 to 35 days. And the relative incidence was 4.95 in that 6 to 11 days window after vaccination. So the main advantages of self-controlled case series is that we only require cases, no controls. That makes data relatively easy to assemble. And the methods are self-controlled. So any factor that doesn't change at all over time, when I say time, I mean over the period of our observation periods. These are things like sex, location, socioeconomic status, or long-term health conditions. They're all automatically accounted for. And this is important, I think, particularly with COVID safety studies, where the vaccinated and the unvaccinated individuals are often different. we are in this situation where the vaccine coverage is high. So any other kind of temporal effects going on, things like age effects, season effects, epidemic waves, they can be taken into account by modelling. Particularly for COVID vaccination, we might want to take in temporal effects over the period since the beginning of the campaign. We can handle recurrent outcomes within self-control case series. That's not a problem. We can have just single outcomes or recurrent outcomes, and the power is often good when those vaccination risk windows are short. It's perfectly flexible in handling multi-dose vaccinations. So we can just set up vaccination risk windows and give them different factor levels for each dose, or you can assign them the same factor levels. We can put multiple risk windows after a dose, and so to capture the changes in risk by time since dose. One thing I haven't put in my talk was about overlaps. So it's quite possible that these vaccination risk windows might be longer than the time between dose 1 and dose 2. That can be handled in various different ways. One possibility is just to let dose 2 risk window take precedence and just stop the dose 1 risk window at the time of dose 2. Another possibility would be to then assign yet another factor for the overlapping period. And I think that is probably the preferred method there. But there are limitations and disadvantages to this method. So the length and timing of vaccine risk windows may need careful thought. And certainly in this situation with COVID vaccines, everything's so new. Whenever there's a safety concern, it's not necessarily immediately obvious how long these vaccine risk windows should be. Temporal confounders can bias the results if they're not taken into account. And it will only give estimates of relative incidence within individuals. So absolute risks are not estimated. And self-control case series has some strong assumptions. So those assumptions, first of all, the outcomes must not influence the timing or occurrence of subsequent exposures. This is probably the main problem for many trying to do self-control case series studies. Now, if it's only a short-term dependence, so if there's just like a short delay in vaccination, then that can be allowed for easily. But if there's a longer term dependence, then there is an extended method that can handle this situation, and I will talk about that in a minute. The second assumption is that outcomes should not influence the duration of the observation period. Now, this can bias self-control case series studies in either direction. Quite often, that bias just cancels itself out. So the simplest thing to do is just a sensitivity analysis where we remove those individuals whose event, say, results in death or might have a censored observation period. And that's usually quite informative. If there's little difference in the estimates, then we probably don't need to worry about that second assumption. If the estimates are quite different from that sensitivity analysis, again, there is an extended method that can handle it. And thirdly, the timing of outcomes should be independent. The easiest way around this is just to study the first events. So that really awkward assumption that the event should not affect the occurrence or the timing of the subsequent vaccinations, it's quite often not the case. So I'll just run off some of those situations. So delayed exposure. So vaccination might, say, be delayed until recovery. Terminal events. I mean, it might be that after an event, vaccination is impossible. And certainly this is a situation where the event itself is death. Contraindications. So vaccination cannot be given after an event, something like anaphylaxis. Reverse causation. So if the event causes or inhibits vaccination, so say the occurrence of an event puts an individual into a vaccine eligible group. I know with COVID and bleeding events, there was certainly a question whether this was happening in the UK. I don't know what my co-workers decided in the end, but it looked like after somebody had had a bleeding event, then they were getting vaccinated within a fairly short time frame afterwards. So there was a question over whether having that event actually put them into the vaccine eligible group and brought vaccination forward for them. And sampling sometimes has been an issue, say if a vaccination history is only taken at the event time. For most of these situations, if we're lucky, the self-control case series can be adapted. So a very easy situation to deal with is when there's only a short-term delay. So if the outcome only temporarily delays vaccination, then we end up with a sort of deficit of outcomes in the period preceding vaccination. We always know the direction of the bias with these events, and in this situation where there's if there's a delay, then the relative incidence might be biased upwards. We can just correct this by including a short pre-vaccination window. But if delays are only very short term, this often results in very minimal bias, and if it really is very short term delay, it can probably be ignored. So just in an illustration of including a pre-vaccination period. So if we have the timing of vaccination where the blue arrow is, it's just like adding another risk window into our analysis, but before vaccination. And then hopefully just that should correct the bias in the relative incidence. So going back to that MMR and convulsions example, in the diagram there, it looks like there might be a deficit of outcomes in the 2 weeks prior to vaccination. So if a child had had a convulsion, then it's likely that their mumps, measles and rubella vaccine would have been delayed. So we add in this extra window from -14 to -1 days before vaccination. We see that the relative incidence is low during that period. And the relative incidence in that 6 to 11 day window, where we can see that spike. With the corrected analysis, the relative incidence has been pulled down just a little as compared to an analysis with no correction. What about the more awkward situation of longer term dependence? So for long-term delay, or if the vaccination cannot occur at all after an event, then we get around this by using only post-vaccination time. When we do this, the post-vaccination windows must be finite, preferably short. So we need to be in the situation where risk returns to some kind of baseline after vaccination. So if there's only a single vaccine, then that's fairly straightforward. We can just redefine our observation period from the time of vaccination up until the end of the study. Originally, this was kind of conceptualized for the situation where the event itself was death. Now, even if the event is death, we want to continue those observation periods all the way up to the end of the study. Remember that second assumption was that the observation periods should not be influenced by the event itself. And we just get around that by extending all the way up to the end of the study. And since there's only one exposure, or the final dose has been observed, then the subsequent exposure history is known and self-control case series is valid. Of course, for COVID vaccines, we're in a situation where we have most of the time 2 exposures, although as Anne has noted, we might now soon be in the situation where we have 3 exposures. but for now, we'll just consider a 2-dose vaccination schedule. So our relative incidence for that second dose risk period can be estimated as for a single exposure using only the time after dose 2. That's fairly straightforward. But what about those people who had an event before the second dose? So what we do in this extended self-control case series method is that we aim to proceed as if there had been no second dose. So our relative incidence for the first dose is estimated using study time after dose 1. However, what we need to do is we pull the relative incidence during the dose 2 risk window down to 1 in line with baseline windows, so that it kind of mimics the situation where we've only got a single dose. We do this by replacing any event that occurs during that second risk window with an unbiased estimator, which is 1 divided by the relative incidence for the second risk period. So to put that into pictures. So if an event occurs after dose 2, then we can make inference for dose 2 just using time after dose 2, fairly straightforward. For dose 1, if an event occurs during that second risk window, there's a kind of like a weighting on the event, which is 1 divided by the dose 2 relative incidence. So our estimation using this extended method, it kind of happens in layers. So we're kind of first estimating for dose 2 and then for dose 1. And if the event occurs before dose 2, that person can't contribute at all to dose 2 estimates, but only to the dose 1 estimates. So what we end up doing is we use some individuals twice if they have 2 doses. And for individuals who have only 1 dose, then we only use them once. So we use an iterative procedure for estimation of both dose effects. So just estimate dose 2, estimate dose 1, estimate dose 2, until we kind of reach a solution that works. And because we're using some people multiple times and some people just once, then the standard errors need to be estimated, for example, using bootstrap methods. Age and period effects can be incorporated easily. These are never censored. And I know this is a rather complicated method to get around this that I'm describing, but there is an R package which does this in just 1 line. So it can be fitted relatively easy if you're comfortable using R. There was also a simpler method around this. So if the doses are known to be separated by a minimum interval that's longer than the risk window, then a much simpler method is available. So this is just a standard self-control case series method with the observation equal to that minimum interval between doses. So for COVID, I think we usually take our minimum interval as 19 days, say for the Pfizer vaccine. So we would just simply start our observation period from the time of vaccination and end it 19 days afterwards. So this is very much like a self-controlled risk interval design using the post-vaccination time only. So just to put it in illustration. So yes, we know what our minimum separation between doses is with the green dotted line. So we just need to change our observation period to match that. We can completely ignore that dose 1 in this illustration where there was no event. That doesn't contribute anything. And we're just using that minimum separation to determine the length of the observation period. And there's just a short example of where this was used in a study of sudden infant death within 3 days of penta or hexavalent vaccination. So we've got the more complicated extension estimates under the modified self-control case series and the minimum separation estimates in the right-hand column. So the modified or extended self-control case series, we can use all the data. So that was applied to all 318 cases of sudden infant death here. Using the minimum separation method, then that was only applied to 90 of the 318 cases where those events happened to occur within that minimum separation window. Actually, only 8 deaths occurred within 3 deaths at 3 days of any dose. And we can see that it didn't look like there was a particular increased relative incidence. So brief summary, self-control case series is being used widely for studies of vaccine safety. The main issue is the assumption that the occurrence of events should not influence subsequent vaccination. And I've presented some of the options to circumvent this issue, including the addition of pre-exposure periods where we've just got a temporary delay, or a temporary period where the COVID vaccination can't happen, or using time after vaccination only, where we have this adaptive method. And I'll just put the web address of the self-control case series website, which does point to code for ARS data and SAS. Okay, so that's the end.
Thanks, Heather. And our final speaker before our panel discussion is Dr. Mark Schuchart, Professor of Biostatistics, Biomathematics, and Human Genetics, University of California, Los Angeles, California, US. Mark.
Hi there. Let me make the requisite. Let me switch my screens over. And let me know when they're up.
They're up.
They should be up by now. I'm here on behalf of the Evaluating Use of Methods for Adverse Events Under Surveillance, or the UMAIS Task Force, which is a working group within the Odyssey community. In terms of my disclosures, my participation in Odyssey and partially in the UMAIS project is supported through a contract from the FDA and also an interpersonal agreement through the US Veterans Association. Further, I do contract with Janssen Research and Development, which produces a COVID vaccine, but my contracts with them is neither related to COVID nor the work that I'm going to be presenting today. UMAIS itself is what I would like to call an empirical benchmark study, which builds upon Odyssey's prior work, where we were looking at the evaluation of comparative for drugs effectiveness and safety methods that was recently published in the Harvard Data Science Review. And the idea behind an large empirical benchmark study is to systematically evaluate the statistical performance of different epidemiological methods to decide which methods and which choices within those methods are most reliable, in this case, to identify vaccine safety signals in the real world setting, using observational data, which has been opportunistically collected and is fraught with both known confounding, but more important, huge amounts of unmeasured confounding, which can certainly change the operating performance of the methods that we're going to use. One can systematically reduce most vaccine safety surveillance methods into 4 different components. The first component is a construction of the counterfactual. From this counterfactual, we will get what is the expected number of counts of events that we're interested in for individuals without vaccination, that we could then compare, in a sense, to the observed counts for individuals who have been vaccinated. The second component is then defining a time at risk. This is the time of study under which these safety events can occur. Given those 2 components, we also need to define a test statistic that we're going to estimate, such as a relative incidence rate ratio. And then once we have that test statistic, one needs to set up a decision rule, which will then use to classify which of those test statistics are identifying a safety signal from the non-signals. Let me first start with different ideas on counterfactual construction. And in this large-scale empirical study, we'll look at 4 different counterfactual construction approaches. All of the, well, 3 of these 4 of these have been broached upon in previous talks. There's the case-controlled design, which is really asking how often are patients who have the event of interest vaccinated versus unvaccinated. Also, Dr. Garcia brought up the contemporary non-user comparative cohort method, which is really trying to ask how often do events occur in similar but unvaccinated counterfactual patients. And there are a number of variants that both Dr. Garcia and Dr. Butler mentioned in this cohort method. Some of these variants that are important, particularly in terms of the unvaccinated patients, is how do we choose the unvaccinated patients? Specifically, when do we begin their time at risk? When do we anchor their inclusion in the study? Is this anchored on another type of healthcare visit, which we will capture in our data, on a calendar time, or some other criteria? And then there are choices on how do we decide who amongst the counterfactuals are similar to the factuals. So you may match or not on things like age and gender, or on a large scale of other baseline characteristics that we have for those individuals. There's also the comparative rate estimates, which is the historical rate estimates, which is asking if we look back in the past, how often did our event of interest occur in very different patients in a very different time period? And there are a number of variants here which become quite important, particularly in the historic past. What is the anchoring? How do we select who those patients are? Would we stratify or not our relative rate estimates on the age and sex of our historical versus contemporary patients in those controls? And finally, as Dr. Whitaker mentioned, that we're going to look at self-controlled case series. And the counterfactual here is really how often did or do events occur in the same patient, but over different times. There are a large number of variants of these. In particular, we're going to look at about 17 different variants, which were drawn from the literature across these 4 different designs. Now let's turn to specifying a time at risk and the specific test statistics that you might be interested in estimating. In this case, we looked at 3 different time at risk categories. 0 to 1 days, so immediate after the event, 1 to 28 days after vaccination, which is going to be most of the analysis that I'm going to talk about today, and 1 to 42 days after vaccination. Also within time at risk, as has been discussed several times, is sort of the dose definition. If we have multiple dose vaccines, are we looking at what happens after the first, after the second, or some composite time between those doses? There are many choices in the specific test statistic that you would like to estimate. In particular, we could look at the effect size estimation, specifically in these, the incident rate ratio for the self-controlled design, a hazard ratio for the comparative cohort methods, an odds ratio for the case-controlled approach, or we might also use something based on just the log likelihood ratio itself, which is very common in vaccine surveillance. There's a body of literature looking at this log likelihood ratio that will allow correction for multiple looks at the data over time. Or your alpha spending, particularly amongst these are the maximum sequential Poisson ratio test, or max SPR approaches. And in terms of these test statistics, we'll evaluate them both with and without empirical calibration. And empirical calibration is an approach that accepts that there is a large amount of residual systematic error in these estimates because the data are opportunistically collected and a huge amount of measured confounding. And so we will inject negative controls and use the distribution that we find for these test statistics under the negative controls to help control for the amount of systematic error that might still exist. Finally, in terms of the performance metrics, we need to define a decision rule that allows us to classify signals from non-signals. Kind of the traditional approaches when you're looking at your estimates themselves are the bias and the variance, for example, the mean squared error of your test statistics. But that mean squared error is actually a convolution of two things. There's the sampling error that we normally think about when we develop statistics, which the sequential approaches are there to help us adjust, but it's a convolution of both that sampling error and the residual systematic error. So we might want to deconvolve that and look at what is the relative amount of residual error across these different designs. And in terms of those decision rules, we'll also look at type 1 and type 2 error rates. I know this is a very large audience, so I'd like to give a little bit of background that will make some of our results a little more clear. So a type 1 error is when one claims that there is a safety signal, when that signal itself really is not true. As that type 1 error rate goes down to a smaller value, we call that method very highly specific. In general, when there is only sampling error, in a frequentist setting, we design our tests and our decision rules such that that type 1 error rate is fixed at, say, a nominal 5% level. But with unmeasured confounding, that can be very different. In addition, there's type 2 error, which is when you fail to claim that there is a signal when one really exists. And when that error rate gets really low, we talk about a very sensitive method. Ideally, you'd like your sensitivity, or at least your type 2 error rate, to go down to 0, meaning you have 100% power. In terms of power, as we're rolling out vaccines, we'll also look at a measure of timeliness. This is the amount of time it takes to achieve a certain amount of power. We're going to look at this in the real world evidence setting. The exposures of interest, at least initially, will be historical. We'll look at the introduction of the H1N1 pandemic in vaccine from 2009, a couple different variants of seasonal influenza from a season or two ago, which give us sort of representation of what's happening in rollout in a large population. And of course, 2 multi-dose vaccinations, zoster and HPV, to get an idea on the single versus multiple sets doses. The data sources that we're going to run this experiment in are 4 very large US claims databases and a very large US EHR database. And for each of these exposures and each of those data sources, we've constructed a set of about 100 different negative controls. So these are negative outcome controls, meaning they're not related to any of our exposures of interest. And they've been picked so that they have a similar prevalence to the outcomes of special interest for COVID vaccination put forth by the FDA. As close as possible match severity. And these have gone through extensive clinical review. For each of these negative controls, we'll also impute known positive controls. We'll inject safety signals at a known level so we can get an idea of what the power levels are. This is all done in an open science setting. It's all been pre-specified with a registered protocol. There's open source analytics, and all of our test results are available to the public at these websites. In total, we looked at 117 million different estimates, and I'm just going to talk about a couple of the results that we found. So first, let's start with the same data. So this is just looking within Optum EHR, the same research question: what is the relative risk of stubbing your toe after you've been vaccinated for H1N1? And I think we would all agree that there should be no direct causal relationship between vaccination and stubbing your toe. But this opportunistically collected data, there's tons of unmeasured confounding in there. Looking at the four different methods, one specific variant for each. And as you can see, the 4 methods for the same question, for the same data, come up with very different answers. Some even appear to identify a statistically significant association for the contusion of toe for this vaccination, to give us an idea that we do have to run this across a large number of negative controls to get an idea of what is the best performance amongst these methods. So let's start by looking at OptimEHR across these 4 different designs, across all of our outcomes, and evaluate what is the type 1 and type 2 error rate for these approaches. So over on the left, we have bars that represent the type 1 error rate. There's a dashed line at kind of the nominal 0.5%. So if there were no unmeasured confounding, all of these methods should return a 5% type 1 error rate. That's how they're designed. And over on the right, we have the type 2 error rates for each of these 4 different methods. You'll immediately see that the type 1 error rates are almost alarmingly high for the case controlled method and using the historical comparator. These approaches tend to generate far too many false positives. What we can add in now is we can use empirical calibration to help adjust for the residual systematic error, in a sense, trying to control the type 1 error rate. So the bar plots under each of these now in red and gray give the calibrated estimates that we find. And this helps to demonstrate that empirical calibration using the negative controls starts to make these different designs much more comparable. After calibration, which remind you is in a sense fixing the type 1 error rate, in this case as close to 5% as possible, the self-controlled case series out of these methods appears to have the lowest type 1 error rate, or is the most sensitive. Let's look at the different approaches for adjusting for systematic error. One is through empirical calibration, and the other is using a sequential or alpha spending type of approach for max SPR. And here we have the type 1 error rates for the historical comparator approach and the self-controlled case series. If we start at the uncalibrated and no adjustment method, we see that we have very high type 1 error rates. If you add in max SPR, so you adjust for alpha spending, you do bring your type 1 error rate down, but it is still nowhere close to nominal. If you can then simultaneously inject calibration, we do start to see that these methods start to return the type of behavior that we'd like to see. And I'd like to mention that my colleague Martijn Schumi and I have recently been working on a calibrated method for max SPRT, which in this case tends to demonstrate the best performance. So we adjust for multiple testing in our alpha spending and adjust for the systematic residual error through empirical calibration. Finally, we'll look at the time to 50% sensitivity, or the power after calibration. And you can see at the bottom that, at least in this example, the self-controlled case series has the shortest time to detection. So for a fixed type 1 error rate, the time to about 50% sensitivity is lower than in the other approaches. I know we're running short on time, so I will just say that these results are more or less consistent across multiple databases and many of the different methods. So let me finish with a number of conclusions. The first is many methods here show large systematic error, particularly type 1 error rates. Empirical calibration does help to restore that type 1 error rate to nominal. That does come at the cost of increasing type 2 error. Empirical calibration appears to have a larger impact on returning the performance that we'd like to see, then adjusting for sequential testing, although ideally you should do both. And after calibration and adjusting for sequential testing, the self-controlled case series appears to perform overall the best. However, overall the best, no method achieves high sensitivity for small true effect sizes. These, time to 50% sensitivity there was for an effect size of 1.5 or 2. Smaller effect sizes, at least on these data, are going to require much longer follow-up. So the recommendations are many methods, particularly the self-controlled, the case control and the historical comparator are positively biased and have many false positives. So you should include negative controls and use empirical calibration. Try to include self-controlled designs when you can. Detecting more than half or 50% sensitivity may actually require accepting a higher level of false positive rates. Instead of calibrating to a nominal 5%, you might opt to use 10% or 15%. And finally, questions that I was not able to address up to this point, but we're working on preprints, are the questions of, does applying methods sequentially, that's the idea of evidence generation and then a more refined evidence evaluation approach, actually improve performance? And how do we have significant power for looking at second doses, and how long does that take? Finally, there are 2 preprints available, and no work is ever done in a vacuum, and almost all of this work is done by other members of the UMEAS task force, of whom I've listed a couple of here. So thank you very much for your time.
Thanks. So in the last few minutes, thanks to all of our panel speakers for answering the questions in the chat. I'm going to call on Dr. Garcia to see whether there's anything else to add to these 3 questions that was directed to him. And invite the rest of the panel speakers to come on video too. Thank you.
So regarding Mark's question on the effect of one dose after a second dose happened, I'm not sure I understand what effect do you refer to. Because for me, an effect is the outcome distribution under 2 interventions. So which are your 2 interventions here? You know what I mean? I know I shouldn't answer a question with another question.
No, I understand your confusion here. It's not a terribly well posed question. Perhaps it's not as relevant for COVID vaccination. Or it might be because of differential immune response. But if there really is, a causal effect that you're looking for the first immunization, that should not be related to the second immunization, but yet takes a while to develop. Is this idea, if it were to exist, is it really identifiable or not? I don't know.
Me neither. The short answer is that if you cannot design a clinical trial to answer that question, probably is not identifiable.
Okay, so I think we're at time, and with a number of questions actually in the chat. I invite everyone to actually contact our panel speakers because they provided you their information on the slides. Feel free to contact FD Best also for any of the questions here. I'm going to open up one last time to any of our panel speakers for any closing remarks. Invite Heather to come on video too, regarding the discussions that we just had. Okay, with that, thank you so much. Thank you to our ESP Vaccines SIG group, Bradley Layton, also for helping us out with this, to all the members. And to anyone who has actually been contributing to this. Once again, feel free to reach out to any one of our panel speakers, and we'll see you next year. Take care, everyone. Bye.
Thank you for organizing this, Hui Li.
Thank you.
Bye.
Thank you.